Okay, let's start. Well, anyway, let's firstly check the attendance. Raymond Cui, 20. Raymond Cui, 20. Raymond Cui, 20. Aradin Ghana, 15. Aradin Ghana, 15. Aradin Ghana, 15. Noor Mohammed Berdibikov, 17. Noor Mohammed Berdibikov, 17. Noor Mohammed Berdibikov, 17. Mohammed Syed Dema, 34. Mohammed Syed Dema, 34. Mohammed Syed Dema, 34. Masudu Zaman, 5. Masudu Zaman, 5. Masudu, huh? Sorry? Anybody? Oh, I see. Okay.
I think he has problem with the connection.
Yeah, I see you. Okay. Oh. Ibrahim Rob Job, 29.
Present.
Okay. Mohammed Tama here.
Yeah, I'm here.
Okay. Maker and Safa, 5. Maker and Safa, 5. Maker and Safa, 5. Solomon Carleton, 6. Solomon Carleton, 6. Solomon Carleton, 6. Sador Dadajonov, 8. Sador Dadajonov, 8. Pardon?
I'm here.
Oh, you are Sador Dadajonov, right? Okay,
Yeah.
got it. Temur Marik Daminov, 10. Temur Marik Daminov, 10. Temur Marik Daminov, 10. Priest David Gilga of 12.
Yes, social.
As Rahman Noor, 14. As Rahman Noor, 14. As Rahman Noor, 14. Mehrab Hossein, 15. Mehrab Hossein, 15. Mehrab Hossein, 15.
Lashin number 6.
Number 6, Carleton.
Yeah. Yeah.
Okay.
Lashi 05, Michael.
Michael M. Safa.
Yes.
Okay. Okay, I got it. Janitor Feeders 21. Janitor's Feeders 21. Janitor's Feeders 21. Ablasim K. Kramas 22. Abraham K. Kramas 22. Abraham K. Kramas 22. B. Theophilus G. Russell. B. Theophilus G. Russell 25. B. Theophilus G. Russell 25. Solomon K. Sawyer 26. Solomon K. Sawyer 26. Solomon K. Sawyer 26. Bethlehem Tirahan Mamo 29.
Yes, 老师, I'm here.
Next, the Kevin Laiken
Yes, Lord.
Asifa
Yes, Lord.
30. Next, okay, I see you. Valery Butuk 31. Valery Butuk 21. 31, sorry. Valery Butuk 31. Anna Akulova 32. Okay. Lawan Takabo Grib Mari. Lawan 33. Okay. Lawan Takab Grib Mari 33.
Yes, Lord. Can you hear me?
I see.
Can you hear me?
Benwar Ikram 34. Benwar Ikram 34. Benwar Ikram 34. Azamat Kalimuin 36. Azamat Kalimuin 36. Azamat Kalimuin 36. Okay. Okay, let's move on to our lecture. Let me share my screen. Yeah, Masuduzana, I have counted your attendance. Don't worry about it. Okay. Can you see the slides? Hello?
Yes, Lord.
Can
Yes,
you?
老师.
Okay. Let's begin. Okay. So last Friday, okay. We discussed something about the embedded systems architecture, okay, meaning about some hardware. Okay, so let's firstly have a brief review about our last lecture before move on to today's new content. Okay, so in last lecture, the one main key point is about the embedded processor. Okay, So embedded processor, it has some different difference from the CPU. Although, okay, the embedded processor is actually evolved from the conventional computer CPU. Okay, so why there are difference exist between them? Okay, it is because that the requirements of the embedded system, especially okay, the embedded system, right? It is application centered, so which means that certain embedded devices are designed for a certain purpose. Also, okay, usually the embedded device has strictly requirements of the volume, power, and so on. Okay. Also, it has some special requirements like the stability, real time, and so on. Okay. All these things make the embedded system need a process for different purpose. So not like okay, the CPU on our computer usually are conventional at least we know that for our personal computer now just speaking they are mainly x86 architecture, right? Although the supercomputers and some high-end servers may use some other architectures, but there it is because they need, for instance, they need high requirements for the scientific calculation and so on. But for our conventional computers, they are meaning just one type of architectures. However, because of such difference, so for the embedded processor, there exist several types of architectures. As we mentioned in our last lecture, there are just speaking, there are 5 typical architectures of the embedded processor, including the MCU, DSP, MPU, SoC, and SOPC. So here, we know that the embedded processor first comes out at the 70s, at the 70s, at the about 1970s, right? So that it is not at the very beginning that all these 5 architectures exist at the very beginning. That's not the case. The DSP, SoC, and SOPC, these 3 things, these 3 architectures actually comes out with the development of the technology for the semiconductor. Because that with the development of the semiconductor technology, we can integrate more and more components to a single chip. While the MCU, MCU itself is what? It is a microcontrol unit, or it is also called a single chip computer. So it is mostly used for control, controlled control machine. So if you go to the factory and see some industrial control system, you may say that MCU are used widely there. Then the MPU MPU is involved from a CPU and is mostly widely used for all types of the embedded systems, and especially we know that the cell phone takes nearly half of the embedded market share. The processors within the cell phones, they belongs to the MPU. While DSP, DSP is specially designed for the digital signal processing. So because of this special functionality, so the algorithm and the code are specially designed. So the hardware are also crafted for this usage. Okay, so all the software and the hardware for DSP are optimized for the digital signal processing, okay, so that it can run the FFT image processing for very good efficiency. The SOC and SOPC, okay. Okay, so that the SOC it means the system and on a chip, right? So that it is because of the development of the technology, so that we can integrate an entire system on a single chip. So here with the SOC, okay, so the modularization, okay, of within the embedded system become a real thing, okay. So that we can think that the SOC achieves a certain function, okay. So like when we do a coding, okay, we can use some libraries, okay. So you can imagine that the SOC is a kind of library, okay. We can just simply use it as one component within when we design an embedded system. While the SOPC, okay, SOPC is involved from the SOC, so that here it has the ability for programming. That means that we can even further modify the functionality of the chip. Okay, so usually we use the FPGA, this tool to do the programming. Okay, so with this programming functionality, okay, it means it's like that. Okay, we can implement our own functions. Okay, so like do on the chip. Okay, so that the SOPC can supply the embedded system designer with a more convenient and flexible module. Okay, so in our last lecture, okay, we mentioned that the MPU, okay, is the most. In this course, we most focus on MPU, okay. For the other types of processors, we just introduce them. But for MPU, we will spend some time to discuss it. So like the CPU, okay, MPU also have the CISC architecture and the RISC architecture. Okay, either CISC or the RISC, okay, they both have the advantages and the disadvantages. Okay. So for CISC, what is the advantage of the CISC? Okay. The CISC, okay, it usually supplies some powerful instructions, so which means that the instruction set, okay, can directly provide more functionalities to the embedded system. However, because the CISC instruction set, okay, it supplies some powerful instructions, okay, but these instructions usually have different lengths. Okay, so it means that the CISC instruction set usually do not have a fixed instruction length, okay, and format. Also, okay, because of they have such powerful instructions, okay, CISC instruction set are also various. So all these things makes it is inconvenient for pipeline execution of the CISC instruction set. Okay, so the typical CISC architecture is x86. Is RISC. RISC, okay, so reduced instruction set computer. So comparing with CISC, RISC have limited simple instruction set. So it contains only the most frequently used instructions. So they do not have complex instructions like the CISC. Therefore, okay, the ISA instructions have fixed instruction length and format, and comparatively, it have fewer addressing models. Also, for each instruction, okay, its execution time is short. Okay, so it is reasonable, right? Okay, comparing with a complex instruction. Okay, for instance, the length is different, right? Also, okay, with a different addressing model. So of course, this simple instruction needs less execution time than a lengthy complex instruction. So it is convenient for the ISA instruction to be executed with pipeline. Of course, they have its disadvantages. Okay, so they do not have the instruction set of ISA do not have such powerful functionalities like the CISC. So to mitigate such problem, okay, usually ISA MPU okay, is equipped with a large number of registers. So in other words, okay, it will use more simple instructions and with these registers to achieve the functionalities of a powerful, complex instruction in CISC. So the typical ISA architecture includes the MIPS and ARM. Okay, we also mentioned ARM. Okay, ARM. Okay, because after the ARMs, right, the architecture takes roughly 35% of the global MPU market share. So this ARM company itself, okay, is just an intelligence property supplier. Okay, so it itself does not engage in the chip production. Okay, so it just sells the design of the IP core, right? Okay, while the real chip production are done by other chip manufacturers. Okay. So I mentioned that, okay, one ARM MPU, okay, are usually divided into two main components. Okay, one is the IP core, the other is the interface module. Okay, for the IP core, okay, it is the core of the processor. Okay, especially it handles the functionality like the instruction fetching, okay, decoding, execution, and so on. So here, the ARM, it design the IP core and sell the IP cores design to the chip manufacturers. When the chip manufacturer gets the production license from the ARM, okay, then the manufacturer will design the interface module. Okay, so the interface module will connect the core of the processor, okay, with other peripheral devices. Then combine them together, then it is a completed embedded processor. Okay, so this is just a processor core. Okay? Itself cannot be used. Okay, only combine them together. Okay, it is a completed embedded processor. Okay, today let's continue on the embedded architecture. Okay. So last lecture, we mainly discussed the hardware architecture. Okay. So today, we will start to discuss the software. Okay. So let's firstly see this figure, okay, about the embedded OS component. Of course, okay, we know that the system, right, contains both the hardware and the software. Okay. The hardware, okay, we already discussed that it has the processor, okay, memory, hardware interface, and so on. Okay. So here, I need to emphasize one thing, okay? So here, the so-called interface, okay, does not refers to the user interface, okay? Actually, lot of embedded device does not support the UI functionality. For instance, okay, you may know the sensor, okay. For example, suppose it's a temperature sensor, okay. It simply measure the temperature, okay, of its surrounding environment, or measure the temperature of the for example, the machine it is attached, okay, or it measure the temperature of the maybe some patient, okay. And then it simply transfer the temperature information to some control system, or maybe to some other health system, and so on. So during this process, actually it does not provide any user interface to any user. Okay, it just measure temperature and do the transformation. So here the interface the interface between the hardware and the operating system. Okay, so I think that you have learned the operating system course, right? Okay, so what is the component within the operating system that directly operates on the hardware? Which component within the operating system that directly operates or manages the hardware? So within the system kernel, is there any component that can manage the hardware or operates the hardware?
The OS, operating system.
Pardon? Can you speak
Operating
loud?
system.
Sorry, I
Operating system.
I know what means. My question is that what is the component within the operating system that directly operates the hardware or manages the hardware? Of course, it belongs to the operating system, but I want to know. I want to ask you about the exact components within the OS. What is that?
Application.
No, application is at a very top level. It cannot directly manipulate or operates on the hardware normally. Anybody can answer this question?
The kernel?
Pardon?
Kernel?
Kernel, no. It is part of kernel, but exactly what? It is part of source system kernel, but exactly what?
You mean, is it a software or hardware? Which part?
Okay, let me explain it. Okay, so
I
it
mean,
is a
it's
driver
software-
device, or in more detail, the device driver. Okay.
Oh, the
Device
device.
driver, yeah. You know the device driver, right? Okay, so if you, for instance, if you use your Windows system, okay, you go to the directory of the Windows, and you can find a subdirectory, okay, called the drivers, and then you go to the drivers directory, and you will see many .sys files. All these .sys files are the drivers, okay, of the Windows, which actually operates your hardware components of your computer. Okay, for instance, okay, the sound card, audio card, okay, and the keyboard, mouse, and network card, and so on. Okay. So the device driver is a component that within the system kernel that directly operates the hardware. So actually here the hardware interface is provided, okay, to the driver. Okay, then here the embedded OS, right? Okay, it is the embedded system kernel. Then at the top of them, okay, it is embedded applications. Okay. So here, okay, we say that embedded applications, right? So embedded applications, of course, okay, you need to use the hardware, right? For instance, okay, let's say, okay, suppose you write hello world, right? I think that the first program when you learn when you learn some language, for instance, like C or Java and so on, the first program you have written, okay, is about the hello world, right? Okay, so the hello world will be output, right? Will be outputted. Then can you answer me that is there any hardware involved during the execution of your hello world program? Is there any hardware involved during the execution of your hello world program? No? Really? You know that any program, okay, it will, if it can be executed, okay, who can actually execute it? It must be some hardware, right? So anybody can just think. So it involved which kind of hardware components during the execution of the hello world program? Yeah, of course, CPU is one, right? Anyone else? Any other hardware? So before, okay, the instructions, okay, of the hello world program are to be fed into the CPU. Where are the programs code? Where are they? Where are them? Yeah, storage, obviously the memory, right? Then how can the instructions, okay, be transferred from memory to CPU? Through which kind of hardware that the instructions can be transferred from memory to CPU? Yeah, bus. Okay. Then we say that, okay, the hello world, okay, it is displayed in your screen, right? Okay. So I think that okay, also there is some graphic card and also the screen are involved, okay, in this execution, right? Okay. So you can see that even such a simple hello world program, if you want to run it, okay, of course, actually, because that your code actually before being loaded into memory, it also stored in the in your hard disk, right? It's actually hard disk are also involved. So that even such a simple program, okay, if you want to run it, several hardware components are involved. Okay, so that when we discuss a system, either the conventional system or an embedded system, okay, with the software and hardware, they must cooperate together. We cannot say that the software just run by itself. Okay, it must be supported by the hardware. But how can it be supported? Okay, then it is the things we will discuss later. Okay. So here, usually see wondering about why here I see the non-OS and OS. Okay. So here is two embedded software development model. Okay, one is called non-OS, another is called OS. Okay, So here means that the OS model means that this embedded software is developed as part of the embedded operating system. Okay. So in this way, okay, it is part of the kernel, so that it will use the kernel's interface to interact with the hardware. While if you use the non-OS model to develop embedded software, then of course it is not part of a kernel. Then if you want to use some hardware, you must use the hardware interface provided by the hardware. Okay. So anyway, so we will discuss the two models later. Okay. So here today we do not mention it in detail. So in this course, okay, we need to say that okay, we have two centers. Firstly, the embedded, okay, the course name, remember, okay, it is the embedded system and development. Okay, so the embedded operating system, okay, while the core of the hardware okay, is the embedded processor. While the base point, okay, is for the embedded applications. Okay, so this is corresponding to the development in the name of our course. Okay, the embedded system, okay, and development. Okay, so we after finish the study of this course, okay, we need to have some ability, okay, to develop some simple applications that can be used in an embedded environment. Okay, so here, let me firstly have a brief introduction about the history of embedded software. So at the very beginning, the MCU, okay, so it's a single chip computer, okay, they do not have any operating system, okay, they do not have any OS. They simply have some dedicated monitor programs. So these monitor programs behaviors like the OS, okay, it operates the chips. So even now, many single chip computer okay, still use monitor programs for control purpose. Okay. So why? Okay, because we want the low price of the MCU. Okay. Especially okay, MCU are widely used in big factories and as a basic unit of the industrial control system. Okay. For instance, it is the basic base unit of the supervisory control and data acquisition system. Okay. So such system, it usually short for SCDID. Okay. SCADA, sorry, SCADA. Okay. So this system is used to monitor and control the machines within a factory or factories, okay, and provide the necessary information for the manager. So nowadays, where it is used. Then for the high-end embedded system, okay, so it have the enough resource to run the embedded software. But such software, if we want to run it, it must be supported by the OS. So there are some typical embedded OS, including the VRTX, PSOS, VX, Vox, Windows CE. embedded Linux, ARM, QNX, MUSE, and OS2. It should be mentioned that different embedded operating system it supports different software. Okay, I think it's easy to understand, right? For instance, the software, okay, that can be run, let's say our PC, okay. If a software, okay, runs on the can run on the Linux, okay, environment on our PC, okay. Generally speaking, this software cannot be run directly on the Windows system. Okay. Also, it cannot be run in the Mac OS. Okay. So the similar things here. But the problem here that because that the embedded device are application centered and specifically designed for certain purpose, so the embedded OS also have many versions. Okay, specifically for certain kinds of embedded devices. So how to make code can be run compatibly on different embedded OS, actually it is a big problem. So, but here there does exist, it does exist some embedded development toolkits that try to mitigate this problem. Which means, for instance, okay, the code box. Code box is a embedded program development toolkit. Okay, so the source code of the code blocks, okay, you can use C++. Okay, then you use the C++. Okay, but not just C++. Okay, because that if you want to develop some program, okay, for the embedded device, usually, okay, despite of the high-level language like C++ and so on, you also need to use the assembly language. Okay. Anyway, so after you have written the source code of your, for instance, your embedded application, okay, then the code blocks, okay, in its configuration, you can select which embedded platform, okay, you want your source code to be compiled. So generally speaking, code blocks supplies the cross-platform programming, so that you can simply develop your source code, okay, your application using C++ and assembly language. While, okay, if we want to use this program in different types of embedded device, you can simply use this compiler, okay, to compile it for different platforms. Okay, but here I must mention one thing that, okay, even for the same type, okay, of the embedded OS, okay, let's say the for instance, okay, maybe there are two embedded devices and they both run, okay, the VxWorks, okay. However, maybe this one, okay, runs the VxWorks 1.4.1, another, okay, runs the VxWorks for the version, okay, 1.6.2, okay. So be aware about the version number, okay. Sometimes, okay, sometimes the embedded OS can have some downside compatibility, okay. But it is better to compile your code, okay, to the exactly version of the operating system. Otherwise, okay, it might cannot be run on it. Especially, okay, remember that I say that we need some assembly code, okay. Actually, the assembly code is usually the code to directly operate on the registers So that for different embedded OS, okay, the registers to operate the hardware device are different. So there might be some compatibility problem. Okay, so let's have a 5 minutes rest. Okay, so please come back. Let's continue. Abraham, okay, I see. Abraham, let's see. Abraham. I see, I see. But please be on time next time, okay?
OK，老师。
Please be on time next time. Okay, so let's say the software architecture of embedded system. So in this figure, okay, there are 5 layers, but just 4 of them, okay, belongs to the software hierarchy, okay? The hardware layer is not within the software hierarchy of embedded system. If I ask you, okay, what is the hierarchy of the embedded system? Then you can answer me, okay, it have 5 layers, okay, from top to the bottom is the application layer, OS service layer, OS layer, hardware abstraction layer, and hardware layer. But if I ask you, okay, what is the software hierarchy of embedded system? Okay, they are just the first 4 layers. Okay. So in general speaking, okay, the middle 3, okay, the OS service layer, OS layer, and hardware abstraction layer, these 3 layers belongs to the embedded OS, while the application layer, okay, is the application level software. So I think that you may guess out some functionality of the different layers, right? Okay. So here we can say that generally speaking, each layer, okay, is provide some interface for the bottom layer to some upper layer. Okay. For instance, the hardware abstraction layer, okay, it actually provide an interface for the OS layer to operate the hardware. Okay. Also, okay, the OS service layer, okay, it provides some system APIs, okay, for the application to interact with the OS kernel. So anyway, okay, let me introduce these layers one by one. Firstly, the hardware abstraction layer, which is short for HAL, not the India's plain manufacture. Okay, this is the hardware abstraction layer. So this is a layer of software abstraction between hardware and OS. Okay. Still, it is a part of the operating system. So why we say okay, it is a software abstraction? Because that the hardware, okay. So exactly what does the hardware know a command from the user? Okay. So actually the hardware itself can only receive, actually it can only receive the electrical signals, right? So here, of course, okay, as a user, right? We don't want to directly operate the hardware using different electrical signals, right? So then we need some abstraction of the hardware. So this hardware abstraction layer consists of 3 components. Firstly, the bootloader. Secondly, DSP, okay, the board support package. Then the device driver. Okay. So let's say, let me introduce them one by one. Firstly, bootloader. Actually, this one is very similar. Okay, in the bootloader in the embedded system is very similar to the BIOS. Okay, on PC. So you know what is the BIOS, right? BIOS, you know, right? You know it, right? Anybody know it? BIOS. Yeah. So how can you access to your BIOS? So
By
have you
restarting, by restarting the computer.
Yeah, at the very beginning, okay, when you are starting your computer, right? You can press, for instance, F12 or F8 or F4. Okay, yeah. Or anyway, it depends depends on your exact system. Okay. So you can enter the BIOS. Okay. So after you enter your BIOS, okay. What is the functionality of your BIOS? Okay, so what are the things in the BIOS? Okay, when you enter it, you see what? You see what in your BIOS? So BIOS has what things?
You can use it to runtime services.
Yes. Generally speaking, okay, BIOS provides some configuration to your computer's hardware. Okay. So means that you can, in other words, okay, it actually can operate the hardware devices. Okay, basically. So in general speaking, okay, the bootloader, okay, or the BIOS, okay, they are well, exactly what? They are also a program, but a program that run before the operating system kernel runs. So here, operating system, okay, it is also a program, right? You can imagine it is a program. Okay. So operating system, okay, need to be loaded into memory and let the let the CPU to run. Then who loaded the OS kernel into the memory? Okay, it is the bootloader in the embedded OS or the BIOS in your PC. Okay. So this program actually usually hard coded. Okay, hard coded within the bootloader or within the BIOS. Okay. So they firstly when you start your device, okay, or your PC, okay, they complete the initialization of the hardware device. Also establish the mapping of the memory space. After that, okay, the OS kernel will be loaded by the bootloader into memory. Okay, then it's time for the OS kernel to run. Then I say the board support package, BSP. So this component is to abstract the hardware operation for the operating system. Why? Why we need to abstract the hardware operation for OS? So let's say, for instance, the very basic operation, okay, of a program is the memory accessing, right? Either memory read or the memory write. Okay. However, okay, depends on the different memory hardware. Okay, the exact access method, memory access method, are different. So, then can we develop the operating system for all types of this hardware? Of course not. Okay, we have to have some abstraction so that when the OS designer, okay, to design when they design the OS, okay, they don't have to care too much about the hardware details. Okay, so this is why the BSP component within the embedded OS. It is because that the embedded system really have a lot of different architectures. Not unlike our PC, okay, we know that our PC are mostly use the x86 architecture. So, okay, we don't need to use the BSP. Okay? For instance, the Windows, okay, Windows just use the, if you want to do the memory accessing, okay, we just simply follow the x86 architecture document and do the access. Okay. They don't have to care about other architecture. Okay. So although, okay, the functions are similar, okay, still different of embedded operating system have different definition of BSPs. So the exact functionality of BSPs are slightly varied for different embedded OS. Okay, then device driver. Okay. So in this, so here we have just discussed, right? Okay. So in general speaking, device driver, okay, is the one that directly operates the related hardware device. So to the upper layer, okay, like the operating system or some or some kernel, or the, how we say, kernel developer, Okay. So they do not have to face the details of the different hardware components. Okay. So these things are done. Okay. The exactly operating issue and managing issue, okay, are handled by the device driver. Okay. They just use the software interface, okay, supplied by the device driver. Okay. So in general speaking, okay, if you are kernel developer, okay, then you want to use some hardware, okay, you simply check the document of this device driver and use the APIs. Sometimes not called API, okay. You can just say the interface, okay. The interface provided by the device driver and for your coding. Okay, that's it. Okay. We don't have to care too much about the hardware details. Okay, then the OS layer. The OS, okay, operating system, of course, the core functionality of OS is to manage the hardware resources. Then it will provide the system services, okay, for application. For instance, the scheduling, file system, synchronization, network, and so on. Okay. So these functionalities are also provided by our conventional operating system for PC. Okay. So we know that, for instance, the scheduling. Okay. I think that when you learn the operating system course, you must have learned some task scheduling algorithm, right? So can anybody mention something about mention one or two task scheduling algorithm? Yeah, okay. So please open your microphone and answer it. No one? Just say one or two task scheduling algorithm. Yeah, something wrong with your phone?
It's round robin algorithm.
Yes, right. Actually, there are several scheduling algorithms, okay, different algorithms. But actually, for the embedded OS, okay, we also have the task scheduling needed. Okay, while the file system, okay, for instance, the FAT, okay, NTFS, and so on. Okay, the synchronization, okay, because that sometimes we need the event-driven, okay, so that we need the synchronization. Network, okay, also we know that it is very important, okay, not only for PC, but for embedded devices like your cell phone, okay, we also need the network functionality. But despite of these conventional services, okay, the embedded operating system also has its own special features. Okay. For instance, the embedded OS need to have the strong stability. Also, customization, modularization, and real time. So the stability. Stability means that okay, the OS must be run for a long time without any error happen. Okay. I don't know that. I say suppose your PC okay, continue run Windows system, okay, that's Windows 10 for several days. Not possible that okay, maybe your system have to got something wrong and have to be restarted. Okay, it is very possible. So generally speaking, stability is sometimes it is badly needed by the embedded OS. Okay, especially when it is used in some crucial part. Okay, for instance, the control system. For instance, like the control system of the factory, the control system for the weapon, like a missile or radar and something. Okay, so when it is used in the military field or used in the aerospace field, okay, the stability is very important. Also, the customization. Okay, so this is because that the embedded OS is application centered. So of course, it is a customization. While modularization, okay, so it means that sometimes okay, this part just have achieve a certain functionality. So if we want to use it, we can load it into the memory. But if we don't want to use it, we simply we simply discuss it. That's why we need such modularization. Okay, it is because that even for the high-end embedded system, still its resource is comparatively less than a conventional computers. Okay, so we have to load as less things as possible to the memory to run. Well, real time, okay, this one is also a special requirements for certain types of embedded OS. Okay, let us say an example of such kind of embedded operating system. It is the VxWorks. Okay. VxWorks is a kind of real-time embedded OS. So it is developed by the Wind River Corporation in US. It can support several different architecture, including PowerPC, x86, ARM, and MIPS. The most vulnerable features of VxWorks is its reliability and the real-time ability. Okay, so here, the real-time ability, why it is important? Okay, because that when we do the communication, right, we have to have the real-time ability, right? Because that I speak something, okay, then you must be, then you need to hear my voice in time, right? Okay. At the same, almost when I said just as I just finished my speaking, okay, then you need to hear my voice. Okay. Also, okay, now we use the Tencent meeting, right? It is actually a real-time product, right? When I say something, okay, you can hear it. Okay. So for communication, the real-time ability is very important. Also, the military, right? Okay. For instance, when a missile is launched, okay, you will use the radar. Okay, it will use its radar to guide it to fly to its target. Okay, of course, it must be real time. Otherwise, okay, it is meaningless, right? Also, the aerospace field. So the VxWorks, because it's good reliability and real-time ability. Okay, it is widely used in the communication, military, aerospace, and other related fields. For instance, okay, the Mars probe, okay, launched by US, okay, United launched by the NSS, okay. Its operating system, okay, in the VxWorks. Then another typical embedded operating system is Windows Windows CE. Okay, its full name is Windows Embedded Compact. Okay. Of course, okay, Windows system, okay, it is developed by the Microsoft. This one, okay, is involved from the conventional Windows system, so that it cut down some unnecessary component from the conventional Windows system, and so that make the size of the Windows become smaller, and it is suitable for some certain embedded environments. But still, okay, the Windows CE, it can support, okay, the Windows software, okay, still in an environment, in an embedded environment, it can also just support the Windows software. Also, the embedded Linux, okay, like the Windows CE, okay, it evolved from the conventional Linux, okay, by reducing customizing and modifying the conventional Linux kernel, okay, so that the kernel, okay, of an embedded Linux can be as small as several hundreds kilobytes, okay, while the conventional, okay, the commercial Linux kernel for PC nowadays are usually several hundred megabyte. Okay. Even it can be gigabyte size. So anyway, either embedded Linux or the Windows CE, they just leave the very necessary things in their kernel, because that just speaking, the embedded device do not have so large memory, okay, to store to run that bigger system. Okay. We know that, okay, the Windows 10, okay, you can see your own computer, okay, how much memory it takes, okay. Or if you use Linux, okay, you can see, for instance, the Ubuntu, okay, Ubuntu Linux, it also need relatively large memory to run, but not the case for the Linux and the embedded Linux and the Windows CE. Okay, then let's say some OS, okay, run on the cell phone. So firstly, okay, the mostly widely used cell phone system here is, of course, Android. Android system is developed by Google, while the first version of the Android system appeared in 2007, November 5th. So it is an operating system based on Linux kernel. However, okay, it is different. It is not. We cannot say that it is Linux variant. No, it is not a Linux-like system. Actually, it applies an architecture called the software stack. Okay, anyway, so the Google, okay, firstly developed the Android, but then, okay, the Android system is maintained by the Open Handset Alliance. Okay, so still the Android system, okay, is open source. Okay, but for some concrete, okay, system on your own computer, okay, it might not be the open source. Okay, it depends. So I just mentioned, okay, it uses software stack architecture. Okay. So at the very bottom level of the Android system architecture, okay, it is the Linux kernel. Then there is an JVM. So you have learned Java, right? Have you learned Java?
Yes, Laoshi.
Yeah. So you know what is JVM, right?
Java virtual machine.
Yeah. Java virtual machine, right? So
Yes.
that actually, yeah, you remember that when you do the Java programming, okay, after you compile a Java code, okay, so it actually runs within the runs on top of the JVM, okay. So that here
Yes.
it is a similar case, right? So in Android, okay, it builds a JVM based on the Linux kernel. Actually, here it uses some David code. Okay, for the David code between the Linux kernel and the JVM. Okay, if you are interested, you can check the Android systems document. Okay, actually, many research have been done on this part. Okay, because that there are some inherent security problem that exist in the Android system kernel, okay, because that it uses this kernel and build upon build a JVM upon it. Okay, you know that once an architecture is complex, then more complex, then it is more possible that it have some security issue, right? Okay. Actually, many research have been done on this part, okay, to discover some security flaws for the Android JVM and also the David code between the kernel and the JVM. Okay. Anyway, so the Android apps so actually run on top of the JVM, okay, not directly on top of the kernel. Okay, remember that in our PC. Okay, actually we can say that our applications run on top of our kernel. Okay, so we do not have this middle layer, okay, such JVM layer. So anyway, so this complex architecture result in some problem, result in some security issues. Okay. Okay. So anyway, but because of the Android system is open source, okay, so many the cell phone producer, okay, actually modify the open source Android system and produce their own Android-based operating system for their own cell phone. Okay, so as a result, Android-based system, okay, takes more than 80% of the market share, okay, far surpassing the second one is the iOS. Also, okay, the Android system not only be used on smartphones, okay, also the tablet market, okay, it also has greatly grows. Okay. Of course, after introduce the Android, then we need to mention the iOS, right? iOS is developed by Apple. it is based on Darwin. Generally speaking, it is a Unix like system. You know Unix, right? Okay. Actually, Unix Unix system is a very classical operating system. Okay. It appears, I think, the first generation of Linux. Sorry, not Linux. Unix. It appears in the 1960s. Okay, and for the actually for it actually at that time there's no personal computers, right? Okay, usually at that time there are just some huge computers like the workstation and so on. Okay. Of course, the Linux, okay, Linux is a kind of the lightweight Unix. Okay. So from this perspective, that we can say that either the Android and iOS, okay, they are based on they can be we can say that they are they are based on the Unix. Okay, but of course they are. They have evolved too much from the Unix. So the first generation of iOS appeared in 2007, the January. It is even earlier than the first generation of the Android system. Initially, the iOS only support the iPhone. Then it also supports other Apple devices like the Apple Touch, iPad, Apple TV, and so on. Okay, the architecture of iOS include 4 layers. Firstly, the core OS layer. Second, the core service layer, the media layer, and the Cocoa Touch layer. So the core OS layer, we can think that it is the kernel. You can just think it is the kernel. While the rest of 3 things, the core service layer, is actually like the OS service layer we will introduce. That it provide the operating system service, to the top level application. While the media layer and the Cocoa Touch layer are used for support the peripheral devices. Then the iOS, it is closed source. Unlike the Android, which is open source. So of course, there are not too much types of the iOS-based system. It's only be used by Apple. But still, we know that although the market share of Apple cell phone is relatively small than the Android system, but still, Apple get a lot of profits from the iPhone. So anyway, so we can see that the iOS is still is also very successful. Although its market share is small, but the profit is good. Then there are also some other operating system for the cell phone. For instance, Migo. It is a free smartphone operating system. It is developed by Nokia and Intel. It can support smartphone, notepad, TV, and so on. And also, if these devices are all use Migo, then these can cooperate seamlessly. Migo is also based on Linux. Specifically, it integrates the Nokia's Memo and Intel's Moblin platform together. Then the Migo system produced. Then the MIUC OS 2. This one is also an RTOS, okay, real-time OS. It is developed, okay, by the J&J Laboratories. Okay. Then the COS, okay, this is short for the embedded configuration operating system. This one is developed by Red Hat. Okay, you may know the Red Hat Linux, right? Okay. Or the same Red Hat. So the most notable characteristics of the ECOS system, okay, is the kernel configuration. Okay, so remember that if you install a Linux system, okay, you can configure the Linux kernel, right? You do you have the Linux lesson? Linux this course? Linux course, do you have that?
No.
Oh no, okay. Anyway, so if you have some experience for installing the Linux, okay, you know that the Linux kernel can be configured. That means that which means that you can select the needed functionality and the components within the system. So the same things apply here. Okay, so for the ECOS, okay, you can just pick up the needed component, so that which can meet the strict requirements of the resource, right? Because of the limitation of the resource, okay, we just need to pick up the needed system component. So the kernel configurable is also very good for the embedded system. Okay, then let's see the system service layer. Okay, so this layer, okay, is upon the OS layer. Remember that the hardware abstraction layer, okay, provide a hardware interface for OS. Then the system service layer have a similar function, but it provide OS interface to the top level applications. So here the interface is usually called the system call. Okay, you know the system call, right? I think you know the system call. I think that when you learn the operating system calls, that you should have you should have learned the system call API, right?
Maybe we forget that.
So anyway, so system call is also like okay, the API is from a library, okay, but here this is the API provided by the operating system kernel. So the top level applications, okay, use this system calls to access the OS services. Okay. Then in this layer, okay, it works as the link between the OS and the applications. So it provides the user interface. Okay, the user interface can be the command line, okay, user interface. Also, okay, it can be the graphic user interface. Okay. We know that the early version system like the DOS, okay, and early version Unix and Linux, okay, they are all command line user interface, okay. But after then, the Windows system, okay, provides the graphic user interface, okay, and also the modern Unix and Linux, okay, they both provide us with the graphic user interface. Then task management, okay, because that for multitask system, okay, the OS must need to handle the resource allocation, the task cooperation issue. Then a file system, of course, okay, an operating system, okay, need to have a file system. So make it clear the storage method, and also the data structure of the files on the storage. Then the top layer is the application layer. It is at the top of the entire software hierarchy. Of course, we can say that it's at the top of the entire embedded system hierarchy. So it's responsible for the realization of the system function and the business logic. From the perspective of the function, so all levels of the modules on this layer serves applications. So we can say that all the levels beneath it provide services for the application. While from the perspective of OS, each application is a process in OS. We know that when you start an application, the OS will create a process for it. Typically, application runs in a low privilege process state, and use the APIs, the system calls, provided by operating system to interact with the OS. Okay, time is up. Today we finish here today. Okay, see you next time. Bye bye.
Okay, bye, Lashi.